right, we're just about a minute after the hour. Let me get started again. Let me formally introduce myself. First of all, hello and welcome to the UFS webinar for January the 9th, January the 8th, 2026. This webinar is hosted by the National Weather Service and Office of Science Technology Integration. The goal of the webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. You're probably wondering who I am because I'm a new face here. My name is Jason Anderson, and I'm here to help coordinate and deliver this webinar. For those of you that are probably familiar with another face in the past, Alex used to run these in the last few years. Alex has moved on to a new position, so I have taken over this for the near term and hopefully into the future. Feel free to contact us at OSTI if you have any comments or suggestions about how to improve the webinar. I will let you know in the past we have used GoToMeeting. We've shifted to a new platform today called Vimeo. So it's going to be a little different. Should be okay. If you have any comments or any technical feedback, please let us know in the chat. Or if you have suggestions for future as well, we'd be happy to hear those. Do note there is a slight delay of about 5 to 7 seconds on this new platform. So it's not that there's a pause or an internet issue, just might be the way the platform behaves. I do want to very briefly thank Alex for his assistance in the handoff. He actually came back and helped me earlier this week in getting this together. I also want to thank Charlene for helping to bring this together as well. All right, due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the chat box, and we will go through those after the presentation. Presentation should be about 40 to 45 minutes today, followed by Q&A until 4 o'clock Eastern. I also want to note our next meeting is currently scheduled for February the 12th at 3 p.m. Eastern Standard Time. If you have any recommendations for future speakers, if you would like to present at this webinar or you have someone you think would like to present, you can email your recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. You can also reach out to me directly. I am jason.r.anderson@noaa.gov. With that, let's move into our presentation. Today, we have a topic on planetary scale to eddy scale advancements in the NOAA Research Global Nest Initiative. I'd like to welcome our speakers, Lucas Harris from GFDL and Lingzong Zhao from Princeton University. Gentlemen, please take it away.
Thank you so much, Jason. Thank you for giving me this opportunity to speak. So I'm going to be giving a broad overview, and Lin Zhang will be giving a deep dive on a couple of topics. I do want to acknowledge the excellent people who made this all possible, the FE3 and SHIELD teams, my collaborators here within GFDL, as well as many excellent people throughout NOAA and through the broader community. So I gave an overview of the Global Nest Initiative in my last UFS webinar back in March 2023 now, almost 3 years. Just to give a brief overview, basically the whole idea is to create new models for new applications using the tools we have here in NOAA to push the boundaries of weather prediction and of understanding even farther with a focus on extreme weather events. We focus on a couple of different specific implementations, particularly 6.5 kilometer global prediction modeling, 3.5, 3 and 3.5 kilometer global nested models for medium range extreme weather prediction, and the global storm resolving model, as well as pushing into the hectometer and sub-kilometer scales for understanding and potentially even prediction. You'll see more information on the website or this tech note here. Our foundational technology, FE3, the GFDL Finite Volume Cube Sphere Dynamical Core. This is the foundation for all NOAA and NASA global models, as well as new regional applications that are being done. It gives you a number of different facilities to be able to really push forward the boundaries of numerical modeling, be able to get you faster forecasts that are more accurate, accelerating model development, going to increasingly high resolutions, and for many different applications. I'll focus on 2 particular ones outside of the milieu of this talk. One is the excellent FE3-based GEOS being developed at NASA Goddard, being used for a very broad wave applications, especially data assimilation, as well as our partners upstairs here at GFDL, the SPEAR-coupled seasonal decadal model, which has been also used for a very broad range of powerful topics as well. Our particular modeling system is SHIELD, the System for High Resolution Prediction at Earth to Local Domains. This is a unified modeling system, non-hydrostatic FE3, coupled to a modified form of the all-purpose GFS physics. This can be configured for many different applications to show the capabilities of FE3, the FMS frameworks, as well as new components from elsewhere in NOAA. This has a number of different initialization options. You can initialize from GFS or ECMWF analyses. I'll also briefly mention our experimental shield data assimilation system. And this is seamlessly integrated with the longer range predictions that go on here at GFDL. I mentioned SPEAR earlier, also the CM4 and CM5 models, as well as NWS operations and the UFS. In particular, all the science components are shared between all these different modeling applications, drawing from community FE3 and FMS, and we're frequently exchanging parameterizations, validation tools, and just code updates with our partners at NCEP, AOML, NASA, and elsewhere throughout the community. One of the strongest features of FE3 is its flexibility for grid refinement. We offer two different ways of grid refinement. We're going to focus on what we call two-way nesting, which allows both the global scale and storm scale to be consistently represented. There's a number of different powerful aspects to this. In particular, you can use different time steps on different grids, and you can push into telescoping nests as well, all with different time steps for great efficiency. I want to mention also the excellent HAFS model developed by our colleagues at AOML and at EMC, at MDC. Fantastic model that's also using some of these same ideas. There's also the grid stretching available in FE3. This is used a lot by chemistry modelers, both here at GFDL and by our partners in the community. Here's an example from Harvard University and the Washington University in St. Louis. This is a very simple way of doing things, a little bit simpler than the flexible nesting, but it is a very quick way to get towards very high resolution, and it's particularly good for chemistry complex applications like that. So together, there's a lot of different ways to get efficient multi-scale simulation within FE3. Now I want to go on to a couple of different nested applications. Lin Zhang will speak more about Sea Shield in particular. This is our global nested contiguous United States model, 3-kilometer CONUS nest, 13-kilometer global domain. We made a big improvement to this in 2025. In particular, we've seen some excellent improvement in storms prediction and in precipitation. Here's one example. It's a 3-day explicit prediction of a set of tornadic supercell thunderstorms that occurred in the Missouri, Kentucky, and that area. You can see some beautiful supercell storms here. These are, again, were predicted 3 days in advance that correspond to some powerful tornadoes in western Tennessee and I believe also in southeastern Missouri. You can go beyond just severe weather prediction with this, though. This is a 4-day explicit prediction of hurricane-force downslope winds during the LA wildfires. Here's that produced the devastating fires there in the Los Angeles area. And this is something that goes beyond the operational limit of the regional 3-kilometer models, but also has high enough resolution to capture this, much higher than the global models that could not capture this sort of extreme downslope wind event. This shows you the true value, this full spectrum skill for prediction that global nesting makes available to you. Now, one of the best things about working in NOAA is I can work with some of the best scientists in the world, and here's an excellent example of this. Spurred on by our earlier success with the nested MJO prediction, we started doing subseasonal predictions using the global nested approach. Our partners at AOML, they looked at some atmospheric river forecasts that went out to 4 weeks in advance in nested Sea Shield, and they found skillful predictions out to weeks 1, some out to week 2, and even a little bit potentially into week 3. And this was showing also the possibilities to improve predictability if we were to improve the mean state of the moisture fields a little bit more. So this shows how the large scale and the small scales can interact to give you better forecasts and gives you possibilities of what you need to improve. Furthermore, our partners at the National Severe Storms Laboratory, the world's foremost experts in severe weather forecasting, they have been using our Shield and Sea Shield outputs to train a machine learning severe weather forecasting model. The fact that the global nested model, this is a 5-kilometer model in this case, we're giving you explicit convection and ultrafactolicity, really helped them to extend the reliability of severe weather outbreaks out to 5-6 days in advance, with some hints again about severe weather forecasting of these outbreaks even further in time. We can potentially look forward to further advances in large-scale state and its downscaling using the nesting to advance that. The other major global nest configuration, which we call T-Shield, we use this for Atlantic hurricane forecasting. Global nesting is a natural for tropical cyclones, which are strongly interacting between the large scale and the small scale. And this is also an excellent test bed for testing out just free convection within the in the tropical area and how explicit convection interacts with the larger scales. One major thing we've been using it for is, of course, tropical cyclone forecasting, led by our colleague Kun Gao. The T-Shield, and with similar ideas taken and developed independently by our partners developing HAS, have shown for the first time a model that gets both excellent track skill and good intensity skill. As well as promise of better rapid intensification skill on the side of HAS. These are results from 2024, the excellent track skill by both the GFS and T-Shield that year, as well as good tropical cyclone intensity skill. We're also making progress on impacts on wind fields, precipitation, hydrology. There's implications for storm surge and floods. So you see this example from Hurricane Helene a year and a half ago, where you can see these intense rain events in North Carolina being predicted 72 hours in advance, well downstream from where the hurricane was at the particular time. So this shows you going beyond just forecasting X, Y, and maximum wind speed towards forecasting the true impacts on what a tropical cyclone can cause and the human misery that they can create. But we want to go even further than that. We've been dabbling a little bit in sub-kilometer prediction for a while. We've shown some interesting results with an FE3, kind of an idealized FE3 based model, going down to 500 meters for both tornado vortex forecasting or simulation, as well as simulation of structures in hurricane eye walls. We also use this for very high resolution radiative convective equilibrium simulation, going down to even 62 meters. And this is starting us to think, is LES prediction possible? And that's what we want to do for the next step. So the next step has been to work with our partners at the Florida International University and AOML to be able to develop an integrated TKE scheme, 3D turbulent kinetic energy scheme, consistent with the FE3 numerics, seamlessly integrated in. And we've been so far developing this. There's been a paper already in NPJ, a new one coming out in James for a full TKE scheme. This can promise a radical simplification of the model by replacing 1D PBL and the numerical diffusion with the physically motivated TKE scheme. Already, we've seen some interesting results from this. We're running 500-meter nested T-shield over the Gulf region with our multiple nesting approach we had earlier. We're really getting these spectacular convective features both in the eye wall and in the free convection, as well as some of these extreme 100 meters a second gusts. So there's some very exciting possibilities that we can do, both here and our partners can do to apply this model towards better impacts forecasting, as well as for a variety of other phenomena as well, not just for tropical cyclones. The next application I want to mention is X-Shield. This is the experimental shield. This is our global storm resolving model. This is the latest in a 15-year set of GSRMs developed based on FE3, both within NOAA and NASA. This is a 3-kilometer global model. It's relatively simple. We have just a shallow convection scheme, no deep convection scheme. We use mixed layer ocean for simple air-sea interactions that are nudged to analyze SSTs. This is the most efficient non-hydrostatic GSRM in the world. You get 30 minutes a day with 27,000 cores. This is 6 to 10 times as efficient as a lot of other GSRMs. This is highly accurate. You can see the perfect minus 5/3 mesoscale spectrum and this perfect 4 delta X cutoff right here. And I like this inspiring quote by our Nobel laureate, Suki Manabe here. If you keep increasing the model resolution but don't make the model more complicated, I think you will have a great time. And we've already had a great time with this sort of model. We have been able to do unprecedented years-long GSRM simulations in both present day and in perturbed climates. And we just did a new 11-year AMIP simulation with the new version of this model. One, of course, thing you do is make beautiful eye candy off of this. Here's an example. This is a snapshot. This is after 7 months of integration in X-Shield, showing precipitation worldwide. This is a degraded version to fit in this presentation. But I do have some links here that will hopefully be available later, so you aren't distracted during the talk, unfortunately, of some visualizations that are created by me and my colleagues during the 2025 WCRP hackathon, a pan hackathon. We had 70 people here studying different versions of X-Shield, and we were real excited about some of what they were able to find. There's a lot that you can do with the global storm resolving model. Here is just one application, mesoscale convective systems. Now, most GSRMs, some actually don't do very well, but most GSRMs, including X-Shield, get a very good MCS climatology and characteristics compared to traditional global models. See the 25-kilometer model shown here. And there's been external validation of the whole set of what are called diamond GSRMs. Most of them get the correct diurnal cycle of MCS precipitation and the right distribution of them. X-Shield actually did a fantastic job, both earlier 2018 and the last 2021 version, I think this is somewhat fortuitous, in that it gets an excellent match to the observed diurnal cycle of MCS precipitation. So there's many more applications of this. Unfortunately, I don't have time to go over these, but yeah, we have some links on our website. Data assimilation. So my colleague Mingjing Tong and her postdoc Chi Hu, now working at Singapore's Meteorological Service, they've developed a native shield data assimilation system to be able to move forecasts forward, as well as be able to study new ideas for DA. Already, the native DA system has been able to get better forecasts in the corresponding GFS initial condition. They've been exploring non-Gaussian observation error distributions and all-sky radiance assimilation, which allows you to take in observations from high-impact precipitating regions. They've discovered that actually you can use some of these new ideas, as well as using clouds as information for refining the variational bias correction in the existing GFS BC, gives you better larger scale skill, as well as improving low-level humidity and temperature forecasts. So this is in progress. We're working. Mingjing is working with the folks at NCEP to be able to hopefully transition this into operations. Everybody's talking about machine learning these days. Lin Zhang is going to speak a little bit about machine learning himself, but right now I want to introduce this excellent collaboration, a 6-year collaboration with the Allen Institute for Artificial Intelligence in Seattle. They've developed a climate emulator that runs a relatively coarse resolution that gets excellent results, trained on reanalysis or SHIELD. They developed a new tool, the preprint came out just before the holidays, called Hero Ace, which is trained on XShield to be able to take output from a 1 kilometer model and downscale using machine learning to the kilometer scales to get ultra high resolution precipitation and wind information. It's been trained on our XShield 11-year AMIP simulation. So they have a lot of data to be able to process, and they're getting some really awesome results. I recommend checking out the preprint for both this as well for new stochastic ACE. We have a burgeoning interest in hydrological forecasting, too much and too little water. I mentioned the too much earlier. Here's the too little water. This is my colleague Jianhui Chen and her postdoc Donghyuk Yoon, who moved to the Korean Meteorological Agency late last year. This is basically looking at a couple of different flavors or regimes of land-atmosphere interactions and how they give you different kinds of droughts. So you see 2 examples here. The one on the leftmost, that one in China, that I believe is a water-limited drought in which the surface dries out first. The dryness then leads to a heat wave. The drought then leads to a heat wave itself. Alternately, this example in Mexico that I believe is called an energy-limited compound event in which you get the heat first, that dries out the soil moisture, and then you get your drought. So these are 2 different examples of the kinds of flavors, both linked by how much latent heat flux you have to be able to control both the temperature and the soil moisture. There's a nice schematic of both sorts of events here. One thing we also did found is that SHIELD, the 13-kilometer SHIELD, did an excellent job at simulating these transitions between the different kinds of regimes and predicting some of these events up to 10 days in advance, possibly even giving you some indication that you might be able to approach subseasonal forecasting these events in the future. I want to mention PACE, a project that's been rolling along for a number of years now. This is a work to port FV3 and the SHIELD parameterizations into the GT4Pi domain-specific language, basically a dialect of Python. This has a number of different advantages. One of the big ones, of course, being that it gives us the whole Python ecosystem available within the modeling system. So the easy use, the powerful features, and so on. But it also allows us to then compile the code in an optimized fashion, having one code compiles optimized for each platform, CPUs, each possible GPUs. We're talking about ARMs, maybe even FPGAs down the way. Already, the port of FV3 showed some pretty impressive results. NASA Goddard has been implementing this into GEOS. The die core itself, even a relatively coarse C360, that's a 30-kilometer resolution, got a 5x speed up on an A100 chip on Discover. Higher resolutions see even bigger speed ups. This helps speed up the entire GEOS model, the rest of which is in Fortran, by a factor of 2, a little bit more than a factor of 2, even given the bottlenecks of transferring between the Fortran and the Python code. This can be implemented in FMS and UFS also, but we're also working on importing all the parameterizations, the entire model, into Python, into GT4Pi. Already, the whole model has been ported. We're starting kilometer scale aquaplanet runs. It does integrate. We're also going to be integrating the land model soon to be doing more realistic simulations too. 2 more slides. First of all, I want to mention coupled shield. GFDL has been a world leader in coupled atmosphere-ocean modeling for over half a century. We recently, my colleague Joseph Mowalam has taken Shield and has implemented fully within the GFDL seamless modeling system. It's been coupled to MOM6 and SIS2 using the FMS coupler. We started with a coupled regional model from a BIL funded project we had. This is 1 kilometer simulation of a tropical cyclone from a few years from, I believe this is Hurricane Helene, I believe. You can see excellent coupled features here, as well as the intense wind field in the atmosphere, inducing temperature changes in the ocean. We've also taken a spear-like configuration to be able to run 13-kilometer shield in the atmosphere, 25-kilometer MOM6 6 as well with SIS2. And this runs stably for years, so there's an evaluation underway. We also can couple implicitly to the LM4 land model, which gives us all the different stabilities and goodies of the land model, especially hydrology, coastal inundation, river routing, and more. So we're really excited about the sort of things that might be able to give us in the near future. I want to finish off with something a little bit more backwards, a little bit more about the results that we've had. And this is one of the more astounding results I think that NOAA model development can claim over the last decade. Over the last decade, ever since FV3 has been implemented in operations starting in 2019, the GFS and SHIELD, using a multi-year average, have effectively caught up with the European Center on Atlantic track prediction of tropical cyclones. This gap that existed and had spurred a lot of this development is now essentially gone. So this has been a major achievement of the NOAA community. And furthermore, HASS and T-Shield, both of which are getting good intensity and track skill as well. This is the first for these high-resolution hurricane models. And this is not just FE3 that's doing this. This has been a big collaborative effort. Dynamics, physics, and data assimilation holistically developed together by a NOAA-wide collaboration. So I think this is something that really shows just the example of what can happen when people have excellent tools and can work excellently together. And then finally, I want to finish with a picture of the FE3 team. You can see more information at our websites here. I want to also acknowledge the folks within GFDL and the broader community that have made all this excellent work possible. Thank you so much, and I'll hand it over to Lin Zhang for his segment.
Thank you, Lucas. I'm Lin Zhongzhou from Princeton University. I'm on behalf of the GFDL Shield and FE3 team to present our research activity beyond the global numerical weather prediction. My talk will cover these three items. The first one is our effort to move to the 6.5 kilometer global shield, which is the aim for global extreme weather prediction. The second topic I want to mention is about our latest development of the 3 kilometer global next sea shield on the cornerstone prediction. And the last one is how we use AI to accelerate forecasting in GFDL. Let me start with the global extreme weather prediction. Lucas already mentioned that SHIELD is a researcher-focused unified prediction system that designed for a wide range of applications. So at the center of all these applications is the Global Shield. Global Shield serves as the backbone of the Shield model system. The Global Shield offers the superior larger scale circulation backgrounds and provides an excellent global larger scale medium range prediction. So the baseline of the SHIELD model is the 13 kilometer horizontal resolution, which is the same as the GFS. But at GFDL, we take a step forward to doubling the resolution to 6.5 kilometer. The aim for global kilometer scale extreme weather prediction. So building this 6.5 kilometer shield is to create a digital twin of the Earth for the global convective scale medium range prediction. So how the model's resolution impact the forecast extremely especially for extreme weather prediction. So this is an example of the massive scale convective system. So we use the 1 kilometer radar observation as a reference over here. And then we can see that in model resolution 3.25 kilometer, the model can capture the intensity and structure of the massive scale system pretty well. But in a 13 kilometer resolution, like our actual model, we basically lost the intensity of the massive scale system and the structure. But the 6.5 kilometer resolution, which is fell in between, can represent the intensity and structure of the massive scale system reasonably well. So we built the 6.5 kilometer shield which is leverage the superior scalability of every free dynamical core. Then we optimize the physics parameterization to get a decent and good performance across different spatial scales. The strategic goal of developing the 6.5 kilometer shield is not only to deliver excellent prediction of the global larger scale circulation, but we also want to improve the representation of the mesoscale convective system in the global scale. We want to present some result on this about this 6.5 kilometer shield model. So we first look at the global scale prediction by using by examining the cloud imagery from the models and observation. We use the Geo16 full disk image as a reference. You can see that our 13 kilometer models and 6.5 kilometer model can basically represent the larger scale synoptic patterns of the clouds. You can see the frontal system in the mid latitude. Also, you can see the marine cumulus clouds over the ocean and some convective cells over the continental Southern American, which is also you can see some ITCC that well represent the cloud image. If you zoom into some region areas, you can see that the 6.5 kilometer resolution can better capture the detailed mesoscale scatter cumulus at behind the frontal system. And also you can see that there's a bit more marine stratocumulus cloud over the oceans and also resulted much more finer scale convective system over the continental areas. This is some active value for the high resolution model. And then we move on to take a look at the convective scale prediction using these 6.5 kilometer models. We take a look at the resolution impact on the TC intensity. So you can see that this is the TC intensity average from day 1 to day 7. You can see that the high resolution model, the 6.5 kilometer resolution, you can significantly reduce the intensity average up to 84 hours. And up to 84 hours, the performance is kind of mixed. But you can see that if we take a look at intensity bias, the 6.5 kilometer model basically significantly reduce the intensity bias for the entire 7-day forecast. This improvement of the TC intensity can be supported by looking at the azimuthal mean of 10 meter wind speeds and sea level pressures. From these two plots, you can see that when the model goes high resolution, the model can produce a higher maximum 10 meter wind, maximum 10 meter wind speed, and also have a lower sea level pressures. So this is basically, you can see that a high resolution model can produce a higher, more intense tropical cyclones. However, even though we already reached about 6.5 kilometers, we still see some persistent wind intensity bias in our model that can need to be future adjusted. The next, we want to evaluate the quantitative precipitation forecast over the Kaunas area, where we have where the high resolution observation data is available. So I compare the equitable threshold score and the frequency bias of these two model resolution, and we compare these two resolution, and then the difference between the ETS and the bias are displayed on the bottom of the figures on the right hand side. In these two panels, the red colors means a higher ETS, a higher equals threshold score, and higher bias. Generally, a higher ETS score means a better forecast of the precipitation, and the bias which equal as closer to 1 as possible means the best forecast regarding the frequency bias. So basically, you can see that comparing the 6.5 kilometer model to the 13 kilometer model, the high resolution model can improve the ETS, especially for more moderate to heavy precipitation over here. And for the bias, for the frequency bias, you can see that bias can reduce for the light precipitation, which is original larger than 1, and then for the bias smaller than 1, the high resolution model can actually reduce the bias. So this is showcases the capability of a high resolution model that can produce a chromatic scale precipitation more accurately. Especially want to mention that this high resolution can produce a significant higher ETS and better bias for the heavy to extreme precipitation. The next topic I want to present is our development of 3 kilometer global next seashore model on the cornerstone prediction. This model conversion called seashore is an effective way to reach the stone scale. There's no lateral boundary condition, so it's suitable for long-term model integration that leverages the strength of the unified model system framework of the shield. In 2025, we have a major upgrade to the shield model. Without changing the FV3 dynamical core, we update the global domain with our best 13-kilometer shield configuration. And in the nested domain, we basically revise the GFTL microphysics scheme and with the optimization of the radar with activities. At the same time, we also optimize the shear convection, boundary condition, land models, and also the radiation time step. We want to evaluate the composite radar with activity by using this performance diagram. This performance diagram, the x-axis of the performance diagram is the success ratio. The y-axis is the probability of detection. And then the dashed line represent the frequency bias, and the curved solid line represent the critical success rate, success index. So we compare these two model versions, the C3 2023, 2025, and as a reference, we put her over here, show it as a blue dot. You can see that from the 2023 version to 2025 version, the frequency bias actually from minor negative to a positive frequency bias, which is already aligned with the Hertz frequency bias. For the probability of detection, the newer version of C should actually get a much improved on the POD, probability of detection, compared with the old version. However, we can see that there's some trade-off, which is a success ratio or ratio reduced degrees, but this this degradation compared with the POD is much smaller. Eventually, when we take a look at the critical success ratio, this newer version actually have a noticeable increase with CSI, which is the critical success index. So the major contribution for this improvement is we should go to the cloud microphysics improvement during the development of the 2025 version. The frequency bias of the presentation is another important metric to evaluate the stone prediction in the corners. The frequency bias is defined as the total number of forecast event divided by the total number of observed event. From here, that you can see the frequency bias. We are in the log scale. The Hertz model is a bit the highest positive bias frequency bias in this result. But our previous version of CSHO 2023 actually shows a negative precipitation frequency bias. The latest version CSHO provides a consistently higher frequency bias, actually from negative to slightly positive, but still have lower precipitation bias compared with the Hertz. So we participate in the 2025 spring forecast experiment in last year, 2025, and with this latest version of CSU. So we evaluate the model in different time periods, which is consistent with the spring forecast experiment, and also we including the Great Plains areas. So we do the same performance diagram analysis for the radar reflectivity on the left and precision on the right, and we check the different threshold here. Consistently, the newer version of the C-Shield actually have a better performance of the POD, which is consistent with our early development of the C-Shield model. At the same time, when you take a look at the precision, actually the POD, the success ratio, and the CSI are all increased compared with the older version. Regarding the frequency bias, you can see that both this version has a very close to 1 frequency bias, which is ideal. So this development enhance the seizures capability in the stone prediction and is shown in this slides. The last topic I want to mention is how we use the AI to do the weather prediction. This project started since the beginning of the last year, 2025, and we have made some progress using the AI to do the weather prediction. And in the past several decades, the the global larger scale prediction skill has gradually consistently improved. And together with the model's the increase of the model resolution, or also the increase of computer powers and computer resource. We foresaw that we foresaw that the forecast skill will continue to increase following this trend. However, this was disrupted by the emergence of the AI model that in the recent years. This is an example. This is the AI FS model that even though it's very new, it already surpassed the common physical model IFS a lot. So the AI model also only use a minimum amounts of computer resource, which is very small compared to the traditional physical model. So AI model can accelerate the forecasting by cheaper and faster forecast, and it can enable larger ensemble capability, and most importantly, it can improve forecast skill. So at GFDL, we started to use AI for weather prediction. The model we use here is the ACE model, which represents the AI2 climate emulator. The ACE is a machine learning model that can simulate the global atmospheric variability in the changing climates and over time scale ranging from hours to century. This ACE model, why we now started to use this ACE model and why now? Because ACE is the GPU-based accelerated AI emulator. It optimized for the weather and climate scales, which met the GFDL needs. And ACE is an AI emulator with a stable and long-term simulation, and it can simulate atmosphere variability across the subsequent to decade scale. The ACE model have been originally developed in between collaboration with GFDL and ACE AI2 to train on the GFDL Shield models and GFDL CM4, and it also has the capability to train on AI5, which is consistent with the commonly taught AI models. The ACE model can have internally physical consistency, and is open source and co-developed between GFDL and AI2, so it's readily deployed. Most importantly, recently we have GPUs on the NOAA URSA model that we can start to use AI application in weather prediction. So when we started this ACE project, ACE already purchased by AI2 using 80 years of AI5 data, but the resolution is 1 kilometers horizontally, and they only have 8 vertical layers. And they target for climate application most of the research. And because we want to have this model ready for prediction using the GFS analysis data, so we have to retrain this data using different data set. So we decided to use the UFS replay data set. The US replay data set is based on the UFS model and the GFS models. And we use the UFS replay 31 years of data set and divide the data set into training data, validation data, testing data, and inference prediction, accounting for 80%, 10%, and 10% respectively. We use this data set for retraining the model. This is a training strategy using the ACE model. There's 2 strategies here. One is that we train the model purely using the UFS replay dataset and training the model from scratch. And this is we get the best checkpoint from this training strategy, and we use it as a reference for our later development. The second strategy, we use a more advanced tuning strategy. We start from the EI5 checkpoint, and then we fine-tune the model using different learning rates and different forward step. Finally, we get the best checkpoint for the inference of weather prediction. So we compare this latest checkpoint with the reference checkpoint to see how much improvement using different training strategy. This is the 500 hectopascal high forecast skill regarding the ACC and RMSE. I show the reference latest and shield model as a reference here. You can see the for the reference checkpoint, the forecast skill actually much worse than our shield model with a lower ACC and higher RMSE. However, after the different training strategy, we get a best checkpoint, and the latest checkpoint can actually capture up with the shield model's performance, the prediction, the forecast skill in slightly better than the shield model. For the 850 hectopascal temperature, the reference checkpoint actually outperformed the shield model up to 3 to 4 days. Then the reference checkpoint, the inference cannot catch up with the shield model. But after the fine-tuning, different fine-tuning strategy, the model can outperform the shield model for the whole 10-day forecast. This this performance can be seen in other variables, for example, 2 meter temperature, 10-meter rings, and precipitation. We show here is that after the fine-tuning of the ACE model, the model can beat the physical model, the shield physical model, and the improvements are quite substantial that you can see right here. And then we look at the geographic distribution of these three variable here. Compared with the shield model, in the shield model we have some bias regarding the heights and temperatures. But in these AI models, you can see that from the reference and the latest, they both can reduce the bias a lot. For example, over the ocean, we have a high bias, negative high bias, but the ACE model can reduce the high bias quite a lot, especially for this fine-tuning model. And for the temperature bias at the 850 hectopascal, you see a positive bias over in the low latitude, over the ocean, and over the land, but this bias can dramatically reduce in the AI model. And also we see some warm bias over the lands and in the high latitudes, and this bias also reduced a lot by the AI model. So this is showcase a good performance of the AI model in the weather prediction scale. The last I want to mention is how the AI model predict the tropical cyclone. So because the tropical cyclone basically, the check of the tropical cyclone basically regulated by the larger scale circulation, especially 500 hectopascal high. And you can see from here that the reference checkpoint is very close to the physical shield model, even though that previously we see that the reference checkpoint do not have as good 500 hectopascal high forecast skill as the physical shield model. But for the latest checkpoint, we see that they forecast the TC check errors already significantly reduced with these fine tunings. So this tell us the model, the ACE model can be improved by using different fine tuning strategy, and eventually we can have a AI model that can surpass the physical model in GFDL. So this is summary of my slides. Giving the limited of time, we don't have much time, but we want to have more time for discussion. So I'm not going to go through this in detail. So that concludes my presentation, and we are welcome any questions. Thank you.
Lynn John, thank you both very, very much. Great presentation. Looks like we have about 80 people viewing. So please, any questions, feel free to type them into the Q&A. I'll be happy to read them out. And worst case, if not, I guess we can go back to your summation slide here real quick if there's anything you want to add. But let's give it a second or two, see if anyone's got a question. Questions, anyone? Don't be shy. All right, I don't see anything yet. Lynn John, do you want to? I mean, we got a few minutes here. If you want to wrap up your last slide or any other thoughts that both of you have.
Can you hear me? Can you hear me now?
Now we can. Thank you. I don't know what happened there. Sorry, new platform, folks. Lynn John, why don't you start again?
So no problem. Thank you for letting me know. So this is a summary of my slides covering three topics. The first one is global extreme weather prediction, which is we hope to bridge the gap between traditional global weather prediction with global storm without simulation. And I already showed that the high resolution already outperformed the low resolution regarding the regarding the tropical cyclones and continental convection. And the second topic I mentioned is about the condensate storm prediction with the upgrade of the CCO model in 2025. We have some improvement regarding the POD. Actually, a lot of improvement regarding the POD and the success ratio and the CSI in the presentation. So this is improvements based on our efforts in improving the CCO model. And the last topic I cover is about the AI for weather prediction. This AI model is based on the ACE model, and between the cooperation between the GFDL and the AI tool, we demonstrate the AI model can be changed and fine-tuned to catch up with the forecast skill of the traditional models. And we already showcase some results regarding larger scale and regarding tropical cyclones and so on. Thank you.
All right, excellent, John. And with that, we actually now have questions, a bunch of them. So everyone, I'm going to try to go through these as quickly as I can. I believe our first question comes to us from Jill Dong. In the Sea Shield evaluations, is there an over-prediction bias in reflectivity, but an under-prediction bias in precipitations? Apologies if I misunderstood the figures.
Oh, yes. There's some bias for the radar reflectivity. Let me pull up the slides over here. I can share the slide again. Yeah, over here you can see that the frequency bias for the radar reflectivity. This is the in the May 2023 and May 2024. We saw that the frequency bias actually higher in the 2025 version regarding radar reflectivity because go from 1 to about 2. And then for the frequency bias of the presentation, we indeed have some positive bias right now, going from previous negative bias, now it's a slightly positive bias. But this bias actually lower than the Herd bias for regarding the frequency bias of the station.
Okay. Sean Shears asks, what is the possibility for AI to assist with sub-kilometer prediction?
You want to mention about the times?
Yeah. So I actually think there's a lot of room for AI to be able to do that. The problem is that it needs to have a training data set. And right now, there really aren't much in the way like sub-kilometer observations. So basically, the way that I see forward for that is large ID simulation models like the one that we showed to be able to produce some of the data sets. Now, of course, you need to be able to anything to be trained on that would inherit the biases, of course, and the limitations within the model. But in the absence of new observational data sets that would be able to create that high resolution data, I think models are going to be the way to really produce the data for that going forward.
Okay. Forgive me if I'm going to say the name wrong here. Hamaro, are the shield ACE... Sorry, we're getting a little feedback there. Are the shield ACE model weights available?
Oh, the shield model weights right now is still in the in the training status, and we already finished 1 degree ACE model training and the weights in the ERSA system. If people want to use that, you can just directly contact us. But the 25-kilometer ACE model, we haven't finished training yet, so the weight is still not ready yet. But the 1 degree is ready for use for inference.
Yeah, I should find out the Era 5 trained weights and also the weights for the trained on some of the Shield and CM4 configurations by AI2 are made available.
Yeah. Excellent. Bob Atlas asks, very impressive presentation. How close are the NASA GMAO and GFDL models?
Yeah. Which aspect you want to know?
Yeah, so I'm not an expert at the GMAO models, but I do know that a number of the parameterizations are indeed the same, and of course FE3 die core is very similar, configured a little bit differently. The big differences are in things like framework. I know Land Citrus model is very different. GMAO has adopted RRTMG radiation. I know that they also have a different convective parameterization, and they use a couple of different microphysics parameterizations as well. So other than DICOR and some of the specific parameterizations, I don't think they're really that comparable, but that diversity does allow us to explore the areas in which we are specifically interested in. If we were both constrained to using the same model, I think it would restrict what areas, especially what new areas, we'd be able to explore with our research.
Excellent. All right. These both came at the same time, so I'm just going to pick one. From Ariel Stein, can you please provide further details on the inclusion LES?
Okay, the large eddy simulation model. Okay, and this actually curtails, I know, with another Q&A question. There is a paper that Ping Zhu at FIU has published on the early implementation of the TKE scheme in halves. And that was published in the NPJ Climate and Atmospheric Sciences. We are preparing more thorough evaluations. We have a paper that's in review at James, I believe it is, describing the implementation itself, as well as in the future, we will have a paper that will describe more simulations.
Excellent. And this might also go into the other question about the LES from Clark Evans at GSL. Perhaps I missed it, but would you happen to have a reference with more details on the LES scale evaluations, or is that going to begin the paper you just mentioned coming?
Right. Yeah.
Excellent. All right. Let's see. Dom asks, oh, here we go. Gabby Patron, impressive work. Thank you for the presentations. Not sure how you guys can speak to this, but I'll ask the question. How are the recent cuts in staff and projects impacting your work and benefits to society? Being in Colorado, do you look at the snow forecast performance in the Rocky Mountains?
Snow forecast. Maybe the snow forecast on the Shenlin's paper.
Right. Yeah. I mean, we've evaluated snow forecasts in the western United States. We did that as part of our evaluation of X-Shield, a global storm resolving model, and the performance of precipitation in warm climates. And I had actually cut out a slide on that. We don't look a whole lot at the Colorado forecast in particular. I mean, we're here in New Jersey. But we have taken a look at sort of the mean state of forecast performance. We do find that going increasingly high resolution gives you increasingly better simulation of snow in Colorado in particular. We like to say that resolution is paramount when it comes to orographic precipitation. We haven't taken a close look at that specifically, but I mean, if you have interest and if there's people from the community who are interested in taking a closer look, we love to work with you on that.
Yeah, we also use the seashore model to do the snow forecast in the eastern part of the corners. We haven't taken a look at the snows in the Rocky Mountain, but we do a lot of research on the eastern part of the corners, which we saw that the seashore model have some overbias on the snow forecast in the winter. But eventually, we have find solution regarding changing the microphysics. We can mitigate or remedy this overestimation of snow forecast in the eastern part of the corners.
And then Valerie Uden, do you have plans to proceed toward the deep atmosphere approximation of FV3 dynamics?
Excellent question. Yes. So our partners at MDC, formerly the Environmental Modeling Center, they are currently implementing parts of the deep atmosphere implementation, especially the variable gravity. So there's a scientist there who's working on that. We got a pull request into GitHub right now. It's actually showing some nice results on the deep atmosphere applications itself for the upcoming whole atmosphere model, the FE3-based whole atmosphere model. We've actually gotten some interest also from a couple of folks at NASA on implementation of parts of the deep atmosphere approximation. The two big ones that still remain are going to be the 3D Coriolis that we already have early implementation of that available, but we haven't tested that yet, as well as the variable horizontal resolution as you go up. Now it might be a little bit more challenging. But thank you, Valerie. Excellent question.
Two more, I think, that just came in from. I'm going to say this wrong. Narita Marani, great presentation. Can you comment on the status of development of AI models for weather forecasting directly from raw observations?
Yeah, right now we already see some AI models using the raw observation, especially satellites and radar data to do the AI models trainings and prediction. We actually still haven't done such research yet, but I think this is a very good direction in the future that we can directly use raw observation, and to some extent maybe don't need the physical model in the future. To do that. Right now, these two AI model and physical model have to combine tightly together. The AI model have to use the, for example, realize data which have to come from realize have come from physical model to do the AI training. But in the future, may be some possibility that we can use the raw observation directly.
Excellent. From Jun Wang at NOAA, I may have missed this. Are the results from ACE trained with SHIELD data only, or the the E3SM and SHIELD combined data sets?
Oh, the shoe model training here is based on the US replay dataset, UFS replay dataset, which is based on the US model and GEFS model. They replay on the EIFI dataset. This is available on the PSL website. They provided right now up to 31 years of dataset. They are planning to extend to 1949, which will cover about more than 80 years of data.
Yeah, I will mention that that the AI2 folks have published results in which they've trained on ERA 5 reanalysis and also on 1 degree shield climate simulations, as well as the Department of Energy's E3SM 1 degree simulations also. I believe that they should all be available through either Hugging Face or through GitHub. But yeah, that's a separate effort from what we've been doing on our AI shield, what we call.
We have time for one more question if anybody has one they want to get in real quick. All right, I'm not seeing any takers. All right, I guess with that, Lucas, Lin John, thank you both very much. We appreciate you all presenting today. Thank you for your patience. I know Alex had scheduled you back in October and November. We had the shutdown and delay, so thank you for your understanding through all of that. Thank you for your time today. Thank you for working with me and Charlene as we develop the new platform. I think we're just about done today. I want to thank everybody for joining. As I said at the top, we have our next scheduled webinar scheduled for Thursday, February the 12th, 3 p.m. Eastern Standard Times. If you're interested in speaking or have an idea for someone to speak, please reach out to us at ufs.modeling@noaa.gov. You can also reach out to me directly, jason.r.anderson. I emphasis the R because there's about 3 other Jason Andersons in the Weather Service. Without that R, it won't reach me. jason.r.anderson@noaa.gov. Reach out to me. We'll be happy to schedule you. If not for February, we can also have time in March and into the spring. So let me know if you're interested. With that, again, I want to thank our speakers. Thank you all for your time and attention today. And we wish you and one last thing, this will be posted on YouTube. If not tomorrow, first thing Monday morning, that'll be out to the community as well. Thank you all very much for your time and attention to our speakers, and have a great rest of your day.
Okay. Thank you, everybody.
Thank you. Bye.
Thank you. This is great. Thanks. Okay. Bye.